and then we can start.
Okay. So I think we can start. Welcome everyone. Welcome to another Safari Live seminar. Today we're very happy that we host Christina Giannoula, who is here to present her collaborative work with Safari PyGim, an efficient graph neural network library for real processing memory architecture. Christina is an incoming tenure-track faculty at the Max Planck Institute for Software Systems, where she will lead the SPIN research group. She is currently a postdoctoral researcher with the University of Toronto and has received her PhD degree from the School of Electrical and Computer Engineering, National Technical University of Athens. She is also closely affiliated senior researcher with Safari Research Group at ETH Zurich. Her research interests include the intersection of computer architecture, computer systems, and high-performance computing. So, Christina, thank you for being with us. I think we're ready to start the seminar.
Hi, everyone. Hi, Constantina. Thanks for the introduction. Hi, everyone. I'm very glad to be here today to present our research work called PyGim, an efficient graph neural network library for real processing memory architectures. So this work has been done by me, PIM, Ivan, and our colleagues and collaborators from the University of Toronto and the Safari Research Group at ETH Zurich. Let's get started. I will first start with the executive summary of the work. In the meantime, if you have any questions, feel free to ask me and feel free to interrupt me. We have basically explored the graph neural networks. Graph neural networks are very important emerging machine learning models that are widely used in many applications. And a part of these models is basically a part of this execution of graph neural networks consists of some kernels, some computational kernels that are very memory intensive. We found that the memory intensive parts of the graph neural networks dominate the execution time, and these kernels are significantly bottlenecked by memory bandwidth in processor-centric systems like CPUs and GPUs. So this is the main problem we are basically targeted to solve in this research. At the same time, the recent technological advancements have proposed a new technology that is called processing memory. Processing memory, or PIM, can significantly provide significantly high memory bandwidth because it integrates processors and computing cores inside the memory modules. It enables computation exactly where the application data is stored, very close to where the application data is stored. And this technology can provide very high memory bandwidth for the in-memory processors. And as a result, this PIM technology is a very promising computing paradigm for the memory-intensive kernels of graph neural networks. To this end, we have basically designed and we present the library, which is called PyGim. PyGim is a very efficient and easy to use library for graph neural networks that leverages processing memory systems and processing memory technology. PyGim is effective for various reasons. First, we use heterogeneous graph neural networks, and we enable heterogeneous graph neural network kernels to be executed on the best fit hardware, depending on their compute and memory characteristics. We offload them in the best fit underlying hardware. The second, PyGim provides a very high performance because it has 3 levels of parallelism. And at each level of parallelism, we use a different parallelization strategy on the PIM side. And we adapt this parallelization strategy based on the unique characteristics of the graph. We detect the graph patterns and characteristics, and we adapt the parallelization approach based on the input graph, so we achieve the best possible performance that we can get. And finally, PyGim is very easy to use. It is very programming friendly because we provide a handy Python API. The developers can just use a Python API to deploy the graph neural networks, and on the backend, we offload the memory-intensive kernels on PIM devices. And also, we expose to the users and developers as a lightweight auto-tuning mechanism in order to find the best fit parallelization strategy, not manually, but using this auto-tuning mechanism. The proposed auto-tuning mechanism basically configures the best performing parallelization strategy based on the unique characteristics of the graph without the programmer intervention. So our results demonstrate that PyGim provides a significant performance and energy benefits by 3.7 times and 2.3 times over prior state-of-the-art schemes, also comparing over processing memory approaches. And PyGim provides much higher core utilization on the PIM system by 11 times X compared to the utilization that is provided by the PyTorch and the default implementations of PyTorch whenever we run graph neural networks on GPU systems. So our work is open source. We have released the code in GitHub in CMU Safari /PyGim repo. So let's start with the background and the motivation of this work. So graph neural networks are state-of-the-art machine learning model to analyze graph structured data. There are many applications that represent their information using graph structured data, vertices, and edges. And these graph neural networks basically are widely used for drug discovery, fraud detection, and recommendation systems. So let's now see the execution steps of the graph neural networks. These networks typically have a few layers. They can have from 3 to 5 layers, and they are basically process graphs that have vertices and edges, like this, for example, a small graph that I demonstrate here. So this graph is typically stored in memory by using a matrix, adjacency matrix, and this matrix is basically sparse because there are only a few edges that need to be represented with a non-zero element within the matrix. So this matrix basically is correlated with the edges of the graph, so it is very sparse. And for each vertex in the graph, there is a feature vector. So for example, here, for each vertex of the graph, we have 4 features. So in this example, there is also a matrix that is called input feature matrix in the memory. So this is related with the features per vertex. So this matrix is basically dense matrix because for each vertex we have a feature vector associated with each vertex. So as a result, this input feature matrix is dense. So in order basically to process, for example, the features of the vertex 1, as I have here, the graph neural networks will go and look at the neighboring vertices of this particular vertex 1. So in this particular example, the neighboring vertices of 1 is the 2, 4, and 6. So we need to basically, the graph neural networks explore the neighborhood, the incoming edges of this vertex, which correspond to the features that I have here annotated as with a pink color. So these are the features that we need to basically read. The graph neural networks are reading in order to update the feature vector of the vertex 1. So the computation that the graph neural networks do in this step is basically they do a matrix multiplication, which is basically this sparse row of the adjacency matrix with the multiple rows of the input feature matrix. And the output is basically an aggregation results, which is basically an updated feature vector for the vertex 1. So once this aggregation result is computed based on the feature vectors of the neighboring vertices, then there is a second step in the graph neural networks, which is basically a dense step. This is a small neural network that mainly consists of general matrix multiplications, which are basically dense matrix multiplications. And this aggregation result is fed to this small neural network until in the end there is basically an output feature vector, which is basically annotated with blue color here. And this is the feature vector that is related with the vertex 1. So this is basically the execution of graph neural networks. So if we consider all the vertices of the graph, then each layer of the graph neural network has two execution steps. Considering all the vertices of the graph, the first step is called aggregation, and this basically step is a sparse matrix multiplication, because we need to multiply, each layer needs to multiply the sparse matrix with the dense input feature matrix in order to get an aggregation result, which are the intermediate results. And then there is a second execution step in the execution, which is basically called combination. And this combination is typically a compute-intensive step. It has multiple compute-intensive kernels, like dense matrix multiplication. And it is very well optimized for GPUs. So we have basically profiled these different execution steps that we have in each layer of graph neural networks in a high-end GPU. Here I demonstrate the results for an RTX 3090 that has a bandwidth of 900 gigabytes per second. And we found that basically the aggregation step, which is a sparse matrix, dense matrix multiplication, the SPMM, takes significant time of the inference. Whenever we have graph neural network inference, the aggregation step takes around 90% of the time. It dominates the execution. And we have also seen that the core utilization, processor utilization on GPU, it's very low. The GPU cores are very, they are not very well utilized. There is a very low utilization there. We also demonstrate the roofline analysis for the two different steps, the aggregation step and the combination step. So here in this plot, you will see that the aggregation step is memory bandwidth bound. It is limited by the available bandwidth that there is in the GPU RTX 3090 GPU. While the combination step tends to be a more compute intensive, it is not as limited by the memory bandwidth. It is in the compute area. So overall, we found that this aggregation step is significantly bottlenecked by the memory bandwidth, and it dominates the inference time. It dominates the execution in graph neural networks. At the same time, recent technological advances in new computing paradigms have proposed the processing memory architecture. We have focused our analysis in near-bank PIM systems because these systems provide very high memory bandwidth, and we basically need to leverage, we want to leverage this very high memory bandwidth in the aggregation step. So in this near-bank PIM system, the design on a high level looks like this. There is a host processor that can be either a CPU and GPU and can basically host a general purpose. It can host basically standard memory modules, and it can also host PIM-enabled memory modules. And at each PIM-enabled memory module, there is a core that is closely located with one or multiple or a few, typically one or a few DRAM banks. So here in the PIM-enabled memory module, we can assume that there are multiple PIM cores, and we can assume that there is one PIM core associated for one single DRAM bank. And this is a general purpose near bank PIM system. So in this architecture, the near bank PIM cores can access data from their local DRAM bank very fast with very high memory bandwidth. Because there is basically a direct communication path from the PIM core to the local DRAM bank. So in total, the aggregated memory bandwidth that is provided for all the PIM cores in the system, including all the PIM-enabled memory modules, is significantly higher than the memory bandwidth that is provided on the host cores over the memory bus, the common memory bus. So overall, we make the conclusion that the PIM provides a promising solution for the memory-intensive kernel of graph neural networks for the aggregation step, and we want basically to leverage this technology to tackle the problem that exists in the GNN aggregation step. I will next explain the PyGim design. PyGim is a very efficient and easy to use library for graph neural networks where the aggregation step is basically running on the PIM side. PyGim has 4 key components. First, the cooperative acceleration execution. The key idea is that we run heterogeneous kernels of graph neural networks to the best fit hardware. The second key idea is called parallelism fusion or PAF. This idea tries to balance the computation and the data transfer costs in order to provide very high performance on PIM systems, because we have both computation and we also need to transfer data to the PIM devices. We need to find a sweet spot between computation and data transfer costs. We need to find the correct balance. So that's why we have enabled the PAF key idea. The third key idea is called lightweight tuning. The path parallelization strategy that we enable has many different configurations and it has a relatively large search space that we can explore. So we need to basically tune the path strategy with a very effective way. And we need to tune this path strategy automatically without the programmer manually tunes this strategy. So for this reason, we have enabled a lightweight tuning mechanism that finds the best performing path parallelization strategy. And the last key component is a handy programming interface. We have developed this library as a Python API because it is the common API that is mainly used to deploy machine learning models nowadays. And our library is currently integrated with PyTorch. Okay, so let's start with the first key idea of our solution and of PyGim. The cooperating acceleration is a relatively simple idea. We take the near bank PIM systems. We have 2 types of cores, the host cores, which are they have very high compute capabilities. These are CPUs or GPU cores. And there are also the PIM cores. These cores have very high memory bandwidth. And we have seen that the GNN aggregation and combination have different types of compute and memory characteristics. The compute-intensive part, which is the GNN combination, is running on the host cores, while the memory-intensive part, which is basically the aggregation step, it is running on the PIM cores, on the PIM side. So the key idea here is that we offload different types of heterogeneous kernels to the best fit hardware, and we leverage the PIM cores for GNN aggregation. So with this cooperative acceleration solution, there is an important challenge, an important problem that arises, which is basically the expensive data transfer cost. More specifically, assuming that the GNN aggregation is running on the PIM cores, once this aggregation finishes and we have the intermediate aggregation matrix, we need to give this matrix as input. The output of the aggregation is basically the input of the GNN combination. So we need to transfer the data from the PIM-enabled memory modules to the host cores that they primarily use the standard memory modules. And we need to do these data transfers over the memory bus. And similarly, the output of the GNN combination is basically the input of the GNN aggregation for the next layer. So as a result, once the combination finishes, and this combination uses the standard DRAM memory modules, we need to transfer the data again back from the host cores to the PIM cores in order to run the GNN aggregation on the PIM cores. So overall, there is this data transfers that we need to pass the output of one step as input to the next step. And this is the main challenge that we need to basically tackle with the cooperative acceleration idea. So the solution that we use to tackle the data transfers and at the same time have very high compute efficiency and very high compute balance and high performance, the solution that we propose is basically called parallelism fusion, and I will explain this key idea next. So the high-level point and goal of the PAF strategy is that we need to strive a balance between computation and data transfer costs. We need to tackle the data transfer challenge that I described before, but at the same time, we need to have very high compute efficiency and load balance across the multiple PIM cores of the system. And the second challenge that we need to tackle is that because we target basically graphs and the different, there are in real world graphs have different types of characteristics. They have different sparsity patterns and edges. So the solution that we need to give needs to be tailored to the particular characteristics of the graphs so that we have very high performance. So in order to achieve this, we propose a strategy that has multiple parallelization levels. More specifically, we have 3 levels that I will explain. And at each parallelization level, we have different parallelization strategies. So the first parallelization level that we enable is that we have different parallelization strategies across multiple PIM clusters. So the key idea here is that we have multiple PIM cores in the system, and we group the PIM cores in smaller clusters. So we have like a cluster here, for example, we have 4 clusters, and each cluster has 2 PIM cores. So we group them together, and we split the aggregation across the PIM clusters. In order to split and parallelize the GNN aggregation across the PIM cluster, we use edge and feature level parallelism. I will describe more details about the edge and feature level parallelism in the next slides. Then the second parallelization level is how to parallelize the GNN aggregation, the aggregation step between the cores of the same PIM cluster. Here, for example, we have cluster 4, it has 2 cores, and we need a parallelization strategy for the aggregation kernel among the cores of the same cluster. So for this parallelization level, we enable either vertex level or edge level parallelism. And the third level is basically within the PIM core. Each PIM core can support multiple threads. It can be a multi-threaded PIM core. So we need to basically find a parallelization strategy between the threads of the same PIM core, of one single PIM core. So for this reason, we basically enable either vertex or edge level parallelism among the threads of the same PIM core. So the key idea and the key goals of these 3 levels of parallelism is that we need to find a balance between computation and data transfer costs. And for this reason, the edge and feature level parallelism that we enable in the first level of parallelization across the PIM cluster basically targets to improve the data transfer and targets to minimize and reduce the data transfer costs in the kernel, in the aggregation kernel, while the last two parallelization strategies and the last two parallelization levels within the PIM cluster and within the PIM core, they aim to reduce the computation cost. They aim to enable a high compute balance among the cores of the same PIM cluster and among the threads of the same PIM core. So these different parallelization strategies try to basically try to improve different goals. The first one, the data transfers, and the last two, the computation cost. And as a result, in total, with the parallel fusion strategy, we are able to find the sweet spot and bring a very nice balance between computation and data transfer costs. Okay, so next I will describe the details about the parallelization strategies that we enable in the parallel fusion. In order to describe these details, I will go over
Christina?
an example. Yes.
Sorry, before you move on, I have a question in the previous slide.
Sure, yeah. Feel free to ask questions.
Yeah, so when you say that by doing distribution across PIM cluster, you can reduce data transfer cost. So I want to understand the main reason that why we are reducing data transfer cost. Is that because we don't need to move it all, the same copy of data to all clusters, or? So,
exactly. Yeah, you
okay.
can use a very naive strategy that you need to replicate and copy the data across all the PIM cores, for example. So this kind of replicating a matrix across all the DRAM banks of all the PIM cores is very expensive. It has a lot of data transfers, right? So with the key idea of clustering, we don't do replication across all the PIM cores, but we do a partial replication. We replicate some data. Yeah.
Yeah, so exactly. So within cluster, we are basically replicating, right? Because okay.
Yeah, exactly.
Yeah, okay. Now I understood, because when you were talking about clusters, I couldn't understand since there is no intra connection across PIM cores in your baseline. So I couldn't figure out the reason. But now, okay, now it's clear to me. Yeah,
Yeah,
thank you.
it's a good question. Actually, it is not actually a hardware clustering. It is like a virtual cluster that
Exactly, yeah.
Exactly. There's no some feature on the hardware level. We just do it on the virtually on the software level so that we avoid replicating all the data across all the PIM cores. Yeah, these systems have like thousands of cores, so replicating a very dense matrix, large dense matrix across all DRAM banks in 2000 cores or more, yeah, it results in high data transfer costs over the memory pass. So that's why we do this idea of clustering.
Okay, sounds good. Thank you.
Yeah, feel free to let me know if there are any other questions or also in the chat. Okay, so let's see more details, and in order to understand a little bit more of the details, I will have an example. So let's assume that we have a graph with 8 vertices and there are 14 edges, as I have here. So this graph is basically stored with a sparse matrix in memory. So we have an adjacency sparse matrix that it has a size 8 by 8. And the non-zero values are the ones that are the dark gray cells that I have in the matrix. And then we need to do basically, here we assume that for each vertex there is a feature vector, which are the features of the vertex. So for example, one vertex can be a user, and the features can be the age of the user or some preferences that the user has, for example. So apart from the adjacency matrix, there is also the feature matrix that is related with the features. Here we assume that the features are 4. So the input feature matrix is 8 by 4 because we have 8 vertices and 4 features. And the aggregation step is basically an SPMM. We need to multiply sparse matrix with a dense matrix in order to get an updated matrix for the features. So we have the updated features here with a green color. So first we need to basically parallelize this sparse matrix, dense matrix multiplication across the clusters that we enable on the PIM side. So here in this example, let's assume that we have 4 clusters, cluster 1, 2, 3, and 4 as I have. And we need to basically parallelize the sparse matrix multiplication across 4 clusters. We enable edge and feature level parallelism, as I will explain next. So with the edge level parallelism, we basically split vertically the adjacency matrix because we need to split the vertices across the cluster. So we need to split we basically split the adjacency sparse matrix vertically. And because we split the adjacency sparse matrix vertically, this by default results in a horizontal splitting of the input feature matrix because basically the left part of the edges in the adjacency matrix correspond to the top part of the top half of the input feature matrix. So at the edge level partitioning by default will also do a horizontal partitioning on the input feature matrix. So as a result, we do edge level partitioning across the clusters with this way. So we assume that the cluster 1 and 2 will get the first half of the edges, and cluster 3 and 4 will get the second half of the edges. So the partitioning on the graph looks like this. Cluster 1 and 2 take the orange edges to process. Cluster 3 and 4 will take the blue edges to process and the corresponding vertices. And upon this edge level partitioning, we also do feature level partitioning, which also split the features. So assuming that each vertex has 4 features, we do vertical partition, and basically for a vertex, we split the feature vector in 2 different smaller feature vectors. So eventually the input feature matrix has 4 splits, 4 partitionings, 1 for each cluster. So it looks like this. Cluster 1 and 3 will get the left part of the input feature matrix, and cluster 2 and 4 will take the right part of the input feature matrix. And as a result, the partitioning that we do on the graph looks like this. So here, basically, you can see that cluster 1 and 2 share the edges. So they will share exactly the adjacency matrix, but they have different features that they need to process because we have also feature level partitioning. So we basically need only, for the cluster 1, for example, we only need to transfer the green part across the PIM cores of the same PIM cluster of the cluster 1. Similarly, for the cluster 2, we need to basically we need to transfer only the pink part of the input feature matrix and replicate it across all the PIM cores of the same cluster of the cluster 2. So once we do this kind of partitioning, then each cluster will basically do a smaller sparse matrix multiplication, because you can see that cluster 1 has a sparse matrix, the adjacency matrix, which is a smaller matrix than the initial one, but it is still sparse. And then the green part of the input feature is a dense part. So again, the cluster 1 will do a sparse matrix, dense matrix multiplication. So the results that we will get once we do this SPMM look like this. The cluster 1 will basically create a matrix that has a size 8 by 2, because 8 are the number of vertices that it processes, and it processes 2 features. And similarly, cluster 3, 1, 2, and 3, and 4, all of them will create results that are 8 by 2 in this example. And these correspond to partial results. We need to basically assemble the final aggregation output matrix, the aggregation matrix. So in this particular example, in order to get the final matrix, the cluster 1 and 2 are basically partial results that they need to be merged together. And we need to have like a matrix which is 8 by 2 by merging the 2 matrices with the vector with a matrix addition. Basically, we just add each element. We have an element by element addition. And similarly, cluster 2 and 4, these are results that are partial results. They need to be merged again. So eventually, the aggregation result and aggregation matrix that we get in this example, it is a matrix 8 by 4. Yeah, the cluster 1 and 3, they correspond basically to the first two columns of the aggregation result, the final aggregation result. And cluster 2 and 4, whenever these results are merged, they correspond to the last two columns of the aggregation result. So we offload this merging and merging these partial results to the host cores. The host cores can be either a CPU or a GPU basically system. So we offload these partial results merging on the host cores, and the aggregation result will be on the host cores, and it will be basically the input of the next step, which is the combination step that it will run on the host cores. Okay, so once we do this kind of partitioning across the PIM cluster, we move on the next parallelization level, which is within the PIM cluster. Within the PIM cluster, we have multiple cores, and each cluster, as I mentioned, it basically does an SPMM again. For example, in cluster 4, cluster 4 needs to process the blue edges that I have here, so it has a smaller sparse matrix that it needs to process. And it also needs to multiply with the yellow part of the feature matrix that I annotate here with the yellow. So it is basically an SPMM that we need to do again among the cores of the same PIM cluster. So here we assume that basically we look at one cluster and we assume that one cluster has two PIM cores, and we need to parallelize the SPMM among the PIM cores of the same cluster. So the key idea here is that we basically enable two different parallelization strategies. We can either balance the vertices or balance the edges across the PIM cores. So the first parallelization approach that we have in our library is that among the two PIM cores, we equally split the edges, the vertices, sorry. So in this particular example, you can see that the core 1 will process 4 vertices, 4 rows in the matrix, and the core 2 will process again 4 rows, 4 vertices in the matrix. And the other parallelization approach that we also have in our library is that we can also balance the edges across the PIM cores of the same PIM cluster, but we balance the edges at a raw granularity. So here we don't have actually a very perfect balance of the edges, because core 1 might need to process slightly more non-zero elements compared to core 2. So they are very, very close. We balance the edges, so we balance the computation, but it's not like a perfect balancing. Yeah, so here more or less core 1 and core 2 will process a similar number of edges. And then there is a third parallelization level, which is basically among the threads of one single PIM core. And again, this is also an SPMM that we need to execute here. So we use a similar parallelization strategy as before. We can either have vertex or edge level parallelism. So we assume that there are 4 threads within a PIM core. So in this balancing here in this example that we balance the number of vertices across the threads, you can see that each of the 4 threads will process 2 rows. It will process basically 2 vertices. And the second approach, which is basically to balance the edges, you can see that here each thread can process 4 edges. More or less, 5 edges. So thread 1 has 5 edges to process, thread 2, 5 edges, and similarly for thread 3 and thread 4. So here, because there is a shared memory model between the threads of one single PIM core, we can also do a perfect edge level balancing, in contrast to the previous approach, parallelization scheme, which was between the cores of the same PIM cluster. We didn't split the rows across PIM cores before, because the memory is distributed. But here, the threads have a shared memory model, so we can basically split one row across two neighboring threads, so that we have basically a perfect edge level balance here. So in this case, whenever there is a splitting of one row, one vertex across two or more threads, we need to use a synchronization mechanism because the multiple threads are writing and are updating exactly the same data in the memory. So we need to synchronize those writes and those updates in the memory. So in our library, we have two different synchronization approaches. We can either have a lock-free solution, and we can also have a fine-grained locking scheme in order to ensure that the output result is basically correct. We enable this synchronization approach. So that was basically the parallel fusion idea. We have three levels of parallelism, and we use different strategies on each parallelization level. But this path solution and this path idea creates a new problem and a new challenge, which is basically the programmability. As I explained, we can have edge partitions, we can have feature partitions across clusters. We can also balance the vertices or the edges within the PIM cluster. And similarly, among the threads of one single PIM core, we can balance the vertices or we can balance the edges. And we can also have different synchronization schemes. We can also use lock-free or fine-grained locking. So there are many configurations, and there is a large search space that we need to basically try to tune. We need to tune in order to achieve the best performing implementation in our library. So if we leave all this configuration to be done by the programmer manually, this creates significant programmability challenges because the programmer might not be familiar what are the values and how to tune all these different configurations that the path approach that we propose has. And one more thing that we need to consider is that because we basically target real-world graphs, the real-world graphs can have different characteristics. So they can be, for example, regular graphs, as the one that I have here as the first graph. They can also have a power law distribution. So here in the second graph, you can see that there are many edges in one single vertex, but many other vertices of the graph, they don't have edges as well. So this kind of power law distribution. And there are also diagonal graphs where the edges are in the diagonal of the matrix. We can also have block graphs that there are like specific blocks of the matrix that are very, very dense. So all these unique characteristics of the graph create a new challenge that, even in the case that we tune the path strategy, this path strategy not be only one solution for every single graph. There is no one-size parallelization strategy and configuration for all these parameters that we have. Because this basically configuration and how to tune the path strategy depends on the unique characteristics of each graph that we need to process. So offloading all these kind of overheads in the programmer and leaving everything to be manually tuned by the developer is basically not a good strategy. So this is the second challenge that we basically need to tackle in our design. And in order to tackle the programmability issue, we propose a lightweight tuner. The tuner basically tries to automatically tune the path strategy based on the unique characteristics of the graph without the need for the programmer intervention, without the programmer manually tunes the path strategy that we propose. So here are some more details about the PyGim tuner. The goal of this tuner is basically to predict the best performing parallelization strategy without actually running the aggregation, without actually executing the SPMM. It is basically a predictor about the best performing path strategy without actually running the SPMM and without basically any significant help from the developer. So the PyGim tuner takes into consideration the underlying PIM hardware and the characteristics of the real-world graph, and it has the following components. First, there is a hardware profiler. So this profiler it is running only once. We run it only once per PIM system, and these are some kind of micro benchmarks and performance measurements that we need to get in order to see the compute throughput of the PIM cores, in order to measure the memory bandwidth that is available on the real PIM system, and some other profiling measurements that we need to keep them. And again, this profiler runs only once per PIM server, per PIM system. It runs only once in the beginning. It has very low cost. And then there is the path generator component. This path generator generates different parallelization strategies, different path parallelization strategies, and it creates a large search space that we can explore. And then the path generator takes this search space and gives this as input to the performance predictor. So the performance predictor has some metadata information about the graph. It has some metadata information about the hardware, like the host PIM bandwidth, the compute throughput of the host cores, the compute throughput of the PIM cores. So based on the characteristics of the graph and the measurements that it has from the hardware, it takes the different path-generated strategies and predicts their performance. So the predictor will basically predict the performance of different path strategies. And then there is the path selector component that basically selects the path strategy that has the lowest performance, the smaller execution time, based on the results that the predictor gave. So the predictor does not actually run the SPMM. It is basically some models that predict the performance, and then the selector will basically take the path configuration and the path strategy that has the lowest execution time. So eventually, this basically tuner will run once per graph. Each time that we need to do a graph neural network inference, we have the same graph. It runs only once per graph, and it basically tunes the path strategy that we propose. It tunes how many edge level partitions we do, how many feature level partitions we do, if we need to have a balance of the vertices or the edges across the PIM cores of the same PIM cluster or across the threads of the same PIM core. So the overhead of the tuner is only a few seconds. The whole tuning process takes around 30 seconds in our results. And these 30 seconds are only executed one per graph. So you can imagine that in a real application, there are many inference requests from the user. The user can send multiple inference requests for the same graph. So basically, it is only 30 seconds, but in practice, we can serve multiple inference requests for many users for the same real-world graph. The graph can be, for example, a network, a social network in Facebook or some other social networks. So once we have finished with the component, we have automated the process. So we have found the best performing path strategy, and we enable a path strategy that balances the computation with the data transfer cost. And the final key component of PyGim is the interface, because we want to expose this interface, we want to expose our library with a very high level interface. So we use Python for this reason. PyGim basically is a Python library, and it is currently integrated with PyTorch. It can also be integrated with other machine learning frameworks, but so far is integrated in PyTorch. So here is basically some high-level source code on how a user or a developer can use the library PyGim. So first, this part is related with the graph neural network model. So here, basically, the user and the developer needs to define the GNN model, and it is actually very simple. In this GNN model, you can see that there are three layers, three convolution layers. Then the user needs to basically import the library. So here we import the library PyGim and we name it as Gin here. It is a very simple interface. And then in the forward pass, which is basically the inference part, we need to use the PyGim API for the aggregation. So here we call we use the Gin library, the PyGim library, and we call the aggregation step to run on the PIM devices. We give as input the graph, and actually the dense parts are related with the feature matrix. So the only thing that the programmer needs to do is basically to import the library and use the PyGim API that we expose to the user in order to run the aggregation part and offload the aggregation part on the PIM devices. And the final step is that in order to run the aggregation effectively, we need the programmer also needs to tune. So as I mentioned, the tuning is done only once per graph. So the programmer basically needs to call the PyGim tuner, gives the corresponding data, the graph, and basically some information about the PIM devices. And the tuner will run only once. It will basically find the correct configuration for the path strategy, and then each time we do inference, the aggregation part will basically offload it and it will run on the PIM devices. So here I have a very small demo of our library. We have access to real PIM devices that are from the UpMem company. So here you can see that we run the multiple iterations of the GNNs, and we run the inference part. Basically, the computation is performed on a real PIM device. We offload the computation on the PIM cores of the UpMem PIM devices. So that's a very small demo of our library. And the API that we use is basically just the simple Python API that I explained before. Okay, so maybe I can pause here and let me know if you have any questions so far before I go to the evaluation part. Or
Thanks, Christina. I actually have one question, but I don't know. I wanted to wait until the end, but maybe I can also ask it now. So so you discussed about the two steps for GNN and the aggregation and combination, right?
Mhm.
And you showed the roofline model, and basically the combination step was in the compute bound region. But so my question is exactly actually related to that. So that was really close to the border of memory bound and compute bound. So don't you think that for the combination also we do need to have quite high memory bandwidths?
Yeah, that's a good question, actually. Yeah, I mean, in general, it is actually on the border in this particular GPU. It basically depends on the GPU, right? So this GPU have very high compute throughput and compute capabilities, and it also has very high memory bandwidth, but this is a very high-end GPU. So it depends on the baseline. If we use a relatively older GPU, that point might be different. Yeah, I think that it can be explored a PIM solution, but in general, we didn't offload this PIM solution, this kernel on the PIM side because this kernel basically the PIM cores by default have a relatively lower compute throughput compared to the GPU cores. So I think that the performance, if we actually look at the execution time, will be worse if we float this part on the course of the PIM course compared to executing on the host course.
Yeah, for that particular baseline, I agree. I mean, for that, also considering that you have used UpMem. But in general, maybe if we consider more, let's say, general near bank, the PIM solution, it might worse it, right?
Yeah.
Also, Also the fact that in the aggregation, so we generate a matrix, which is actually temporary, as you said, because that matrix needs to be consumed immediately for the combination. So to me, it makes a lot of sense that we have fused essentially these two kernels together and have them on the same hardware, So that would eliminate significant data movement, no?
Yeah, I agree on that. Like the thing that we need to consider in case of fusion is that as we have the aggregated results that are partitioned across the DRAM banks, this needs to be the input on the combination. That's correct. But we need to do some kind of rearrangement and reordering of the aggregation results in order to run the combination on the PIM cores. It is not exactly the same partitioning that we will give as input for the combination. Even in the case that we offload the combination on the PIM cores, we'll still need to do some kind of reordering and repartitioning there. So in that case, it's not that we completely avoid the data transfers. We still need to do some data transfers. But I agree that there might be some optimizations there that this kind of rearrangement not to be done over the memory pass, but to be done internally within the PIM-enabled memory module more effectively.
Yeah. Okay, yeah, I will save some part of this discussion actually for the end, because I want to know how you want to extend this idea to more general PIM, because OpMem is very specific, is a very specific way of doing near bank also, without any connections or whatever. So, but yeah, let's discuss through the end. Thank you. I'm not sure if there is any question on YouTube, so let me quickly check. No.
I have one question if I can.
Yeah,
please.
sure.
Okay, yeah. So in the slides, you had shown that the initial stage is first we partition the sparse matrix across the different clusters and we perform multiplication. That is which gives us the partial products. And after that, we perform aggregation. So can you tell me what is the sparsity of some of the real world graphs that you tried? Is it like quite high, maybe 70-80%?
It is more than that. It can be up to 99% zeros.
Okay. So then, you will see a lot of rows and columns that are going to be only zeros. So do you actually perform computation or do you eliminate computation of those rows or columns when you are performing this multiplication?
Yeah, that's a good question. So this adjacency matrix is stored in a compressed format. If you have heard about CSR or Q, it is not actually stored as a dense format as I have it here in the slide. I just have it in the slide in order to explain the parallelism and how we partition. But this, for example, the orange part, the first half of the matrix is stored in a CSR format, in a compressed format. We only store the non-zero values. We don't store the zeros and we don't do computation.
Okay. Oh, thank you.
Okay, and then I will move on to the evaluation part. Yeah, so we use a real AppMem server. The server has 16 PIM DIMMs and it has 1,000 of cores. There are 1,992 PIM cores, and each core has 24 threads in total. In practice, we use 16 threads per core in our evaluation because we found that the performance is better with that configuration. Yeah, so the whole system looks like this. There are multiple PIM-enabled memory modules, in total 16, and then each memory module has 2 ranks. So in total, we have 32 PIM ranks, and at each rank, there are 64 PIM cores. Here I have 4 in the figure, but you can imagine that there are 64 cores per rank. Yeah, so these PIM modules are connected to a host CPU. This host CPU is an Intel Xeon server, and we also have the standard DDR modules that are connected over the host CPU as well. We use 3 different graph neural network models, GCN, GIN, and SAGE. And we use 3 different data sets. These are very large data sets. We have, I think, in total, 4 or 5 comparison points that I will explain here. So the first comparison point is that we basically use PyTorch and we run graph neural network inference on the host CPU. This means that both the combination and the aggregation, they are running on the host CPU cores. We don't use the PIM cores in this baseline. And we use the default implementation of PyTorch, which is basically a sparse library. It is optimized. It is an optimized sparse library. Then we compare with some PIM baselines. So the sparse P is basically a PIM baseline where the aggregation is offloaded on the PIM cores. And sparse P is a library for sparse matrix vector kernel. It's not sparse matrix, it is sparse matrix vector multiplication. So we have taken this sparse P library, which is basically a library from the group that we developed 2 years ago, and we run the SPMM as multiple SPMV kernels. We parallelize basically this way, and we use the PIM cores. Then there is the last baseline, which is basically Grante. Grante is a prior work that has been published almost 2 years ago. It is basically a PIM solution for GNN aggregation. This work particularly targets graph neural networks, and they propose a parallelization approach, a parallelization scheme for PIM near-rank PIM solutions that we have basically implemented this scheme, and we compare over their proposal. So let's see the performance results. So here the higher is better. We have 2 different versions of sparse P, sparse 1 and P, and on how basically we configure the SPMV to be used as an SPMM. And then for PyGim, we use 2 different compression formats, either the CSR or the Q format. We support these formats because these are the most popular formats for storing a sparse matrix. So here higher is better. You can see that there are 3 different neural networks for graph neural networks, GCN and SAGE, and we have 3 different data sets. So in total, we have 9 different setups and evaluation measurements. So here you can see that PyGim significantly outperforms the prior baselines. It achieves around 3.1 times better performance over the PyTorch. The default PyTorch that uses an Intel library, and it is running on the CPU. And compared to sparse P and Grante, on average, PyGim achieves around 4.4 times speed. Next, here I demonstrate the energy efficiency. So in this plot, lower is better. We need a lower energy consumption. Here you can see that PyGim significantly improves energy efficiency across all different evaluation setups, different models and different data sets. On average, it achieves 2.7 times better energy efficiency compared to PyTorch, and around 3.3 times more better energy efficiency compared to prior PIM-based schemes. Here in this plot, I demonstrate the scalability. So here we have different configuration of the PIM devices. We use 8, 16, and 32 PIM devices. We increase basically the number of PIM devices, which means that we increase the PIM cores that are used for the GNN aggregation. We use a fixed path configuration strategy for this experiment. We use 2 different data sets. And here we show that basically PyGim library is scalable as the number of PIM devices increases. On average, we have 1.4 better performance as we double the number of PIM devices, which basically means that we more or less double the number of PIM cores. So in this experiment, we have a little bit some characteristics about the path configurations that we have. So here we basically have a sensitivity study on the different aggregation configurations that we have for 2 different graphs. Each bar here has 3 numbers, and these 3 numbers correspond to the following. The first number is the number of edge partitions that we do, which is basically the vertical partitions that we do on the sparse matrix across the PIM clusters. The second number is the feature partitions that we do. Again, this is the the vertical partitions that we do on the feature matrix. And the last number is the number of PIM clusters that we have per device, per PIM rank in practice. So for example, the 132.1 corresponds to one edge level partition. This mainly means that we don't do any vertical splitting on the sparse matrix. We do 32 vertical splits on the feature matrix. And then we have one cluster per device, one cluster per rank, which means that each cluster has 64 PIM cores in this particular configuration. Similarly, the configuration 1, 64, and 2 means that we have one edge partition, 64 partitions on the feature matrix, and we have 2 clusters per device. This means that at each PIM rank, we have basically 64 cores, and we have 2 clusters. So each PIM cluster has 32 PIM cores. So across all the different configurations and different search space that we have seen here, we have this main key observation that I also mentioned in the main mechanism. There is no one-size-fits-all solution. We have 2 different graphs, the proteins and the Reddit, and the best performing parallelization strategy is different depending on the graph characteristics. On the proteins dataset, the strategy 132.1 is the best one. On the Reddit dataset, the strategy 2.16.1 is the best one. It has the lowest execution time. So here, lowest is lower. So based on our analysis and our basically key observations, we have various recommendations in our paper. So next, I will basically describe 2 of our recommendations. So the first recommendation that we have is that if you observe the DRAM architecture, the internal DRAM architecture, you will see that there are multiple hierarchy levels. There is the DIM level, rank level, bank group, and bank level. So each of these levels have different characteristics, and as a result, the architects of PIM technology, PIM architects, can enable different optimizations and hardware optimizations at each level of hierarchy. We can have, like, for example, different optimizations on the rank level on how we transfer the data between the cores of the same rank. And we can have a different hardware-supported strategy on how the data is transferred across the ranks of the same PIM memory module. And if this has been done, and we have different strategies on different hierarchy, then the software engineers can leverage different software optimizations at each different level of the hardware hierarchy. As we did in the PAF strategy, we enable different parallelization solutions for each level. And if each level is also hardware supported, we can also leverage the hardware support that we have at each different level to further improve the performance. So we need to leverage this type of hierarchical design that we have in DRAM, both on the hardware side for the PIM architects and also on the software side for the software engineers that they design libraries and optimize the solutions, software optimized solutions for different applications. And the second recommendation that we do is basically that whenever we talk about sparsity, sparse matrix multiplication workloads, for example, sparse linear algebra, the best performing solution is an optimization strategy and technique is different depending on the characteristics of the graph. Each graph has different unique characteristics, and the best optimization strategy, especially in a hierarchical level, might be quite different depending on the input data that we give. So this kind of strategy creates a new challenge that we also found in this paper, that we need tuning mechanism. And this tuning mechanism cannot be offloaded to the developer and to the user. We need to develop automatic tools, intelligent heuristics, prediction model, compilation and automation tools in order to tune the strategy with minimal programming effort, minimal programming intervention, and achieve the best optimization strategy for different input data with different unique characteristics without basically leaving all this configurability to be done by the developer and the programmer. Last, I would like to go a little bit over the comparison over the processor-centric systems that we have in our paper. Here I show, we compare with the UpMem PIM device with the Intel Xeon CPU, which is basically the host in our, the host CPU in our server. And we compare over 3 different generations of GPU architectures. We have the 1080, 2080, and 3090. These are 3 different generations of GPUs. So here, if we look at the theoretical compute throughput and the bandwidth, these are basically the characteristics by the manufacturer, the theoretical characteristics of the architectures. Yeah, so here you can see that across GPU generations, the bandwidth has been improved. At each basically different GPU generation, the bandwidth over the last 3 GPU generations, the bandwidth has been more or less tripled. Because the GPU architects are also actively working in order to improve the bandwidth on the GPUs and tackle this problem. And we can also see that also in some of the GPU generations, the compute throughput also has been improved, and it has been doubled, for example, from 2080 to 3090. Yeah, so here you can see that the compute throughput of basically the GPUs is much higher than the compute throughput that we have on the UpMem PIM. The compute cores that we have on the PIM side are they have very low compute capabilities. Even in this case, we measure the processor utilization, the core utilization across all these different systems. And here are the results that we have for the Reddit dataset whenever we use int32-bit integers and 32-bit float. So here the key observation is that although the basically GPU architects have significantly worked to improve the memory bandwidth over the years and over the 3 different generations of GPUs, the core utilization still remains very low in GNN aggregation. The GPU cores are utilized less than 1% in most of the cases across all the 3 different GPU generations. While we can see that the PIM architecture is a more promising architecture for graph neural network aggregation, because the characteristics of this kernel are more on the memory side. It's a more memory-intensive kernel. And on average, PyGim executed on a real PIM system achieves an 11.6 times better core utilization compared to running PyTorch on a high-end GPU, like for example in 3090 or 2080. We significantly improve the resource utilization, the core utilization, which mainly basically in practice means that we enable a more cost-effective solution. So there are many more results in the paper that I will not discuss everything in this talk. We have many recommendations for programmers and also for hardware architects. There are many sensitivity studies within the PIM core, across the PIM cores and within the cluster, many scalability analysis, different data types, different compression formats like CSR and COO. We also have a performance evaluation about the training. So far I have presented mainly about inference, but PyGim can also be used for graph neural network training. So please take a look at our paper for more details. It is also available on arXiv, and it is a very insightful paper because we use a real PIM system for this analysis. And yeah, you can also take a look at the code. The code is available at the Safari GitHub. It is open source. So next I will conclude my talk, and after that I will be happy to answer more questions. So in conclusion, I have presented PyGim, which is a very effective and handy machine learning library for graph neural networks, leverages the PIM technology in order to improve performance, energy efficiency, and cost effectiveness in graph neural networks. So the key ideas of PyGim libraries and its benefits is that we need to balance the computation with the data transfer costs. This is basically because for two reasons. Because the PIM technology is a distributed memory architecture. We have DRAM banks, and we need to distribute the data across banks, and the cores access data only locally within the bank. So we have both data transfer cost and data distribution and compute efficiency. We still need to have a load balance between the cores because the cores are very limited in terms of the compute throughput. So if we have very high load imbalance, only one PIM core will do a lot of computation, and it might also create bottlenecks. We need to find sweet spots between compute and data transfer costs in PIM architectures. And because we target a sparse workload, the sparse workload means that we basically have different strategies and optimization techniques per input data. In this particular case, we have a graph that has different characteristics, so we still need to tune this balance between computation and data transfer based on the unique characteristics of the graph. And the key idea is that the second important key idea is that all these tuning and optimization strategies need to be done without the programmer intervention. We need to automate the process without the programmer manually tunes all this and spends all this effort to understand about the PIM technology. So this is what we have done in PyGim, and this is why PyGim is that effective and very, very successful. So overall, the results on a real PIM system demonstrate that PyGim improves performance and energy efficiency significantly over prior state-of-the-art schemes, and it provides much higher core utilization on the PIM system compared to running PyTorch on GPU systems. And these are the QR codes related with GitHub that we have our code, and related with our paper, which is on archive and it is publicly available. So thank you so much for your time, and I'm happy to take more questions now.
Christina, thank you for the presentation. So I was wondering about this different workloads requiring different configurations in your PyGim scheme. So in slide 32 or 31, I guess, you were showing a proteins dataset and Reddit dataset. So I was wondering, like, did you go in depth to see like what affects this trend, different trends? Like, do proteins have less sparse adjacency matrices, maybe?
Yeah, so generally speaking, what it affects this configuration is basically the patterns that there are in the graphs. So a regular graph have a different path strategy that gives the best performance compared to a power law graph, for example. So it is basically the patterns that they affect the computation, but you might see some kind of small differences between different power law graphs as well.
I see, but do you identify like which type of graphs do the protein dataset have, for instance, like each of the datasets? Do you identify?
Yeah, it's a good question. We haven't done this. Sure, it is definitely a good approach to go even deeper and dig into deeper to find this. But generally speaking, this path strategy tunes the characteristics per input graph, right? So we basically tune the path strategy based on the protein dataset and graph that we have. I think, I mean, what is the goal of going deeper? The goal of going deeper is like to try to find a path strategy for all the power law graphs, or trying to find a fixed strategy for all the regular graphs.
Mhm.
So to
Yeah.
group them and basically have a path strategy. This might work. The benefit of this will be basically that we won't need to have this tuner process. We don't need to have it, but
Mhm.
we have a fixed solution by default in our library.
Mhm.
You can do that, but at the same time, the tuner approach that we also propose is only 30 seconds to run per graph. It's very lightweight, right? So I mean, doing this tuning approach might also be more beneficial in the sense that if you have one solution for all the power law data sets, you might still have better solutions with the tuner, because the tuner might still be able to find a better strategy, not the default that you have for all the power law graphs, a better strategy for this particular power law graph.
Yeah, makes sense. If you had one for all power law graphs, you could be stuck at a local optimum for another workload.
Yeah, and also the fact that we have designed this tuner to be very lightweight. We don't explore the whole search space. We basically have some pruning mechanism. We explore on some configurations and so on. So it is only 30 seconds, so I still believe it's worth to develop an automated tuning mechanism instead of like having some default strategy in the library, like saying, for all the power law graphs, I have this path strategy. I believe that it's still worth it to have a tool that on the fly finds it, and also because this strategy might also be different compared to in different PIM systems, right? As also Mohammed mentioned, there are different PIM systems. We target UpMem, but maybe in the future we might have another PIM system from other manufacturers, from Samsung, right? So this path strategy that we have as a fixed one in the PyGim library for the power law graphs might be different across the different PIM systems and PIM generations, right? So the tuner will basically adapt to that.
Okay, thank you.
Yeah, that was a good question.
Okay, thanks a lot, Christina. Any other questions?
Hi, Christina. So I have a question about the parallelism of computing of the graphic. So I'm wondering whether this application is, it's suitable for some 3D architecture because, the 3D has high parallelism of the computing. And what's the difficulty of deploying such graph application on the 3D architecture with high parallelism?
So what do you mean by 3D architecture? I mean, as far as I know, in the HPM PIM product, still there is one core per 2 DRAM banks, right? So it's still
sorry to interrupt. I mean, so for here you have a PIM core and one corresponding DRAM bank, right? So imagine you have a 3D architecture that you have distributed DRAM banks in parallel, and you also have in parallel PIM core or other digital core, and the digital core corresponds to each DRAM bank. And well, this architecture, have more higher performance because you have high parallelism of the DRAM banks and corresponding PIM cores.
I think that PyGim library could also leverage this high performance, right? So the assumption that we do on the architecture level in the PyGim is that each core access data locally from a local DRAM bank, and we have a distributed architecture where there are multiple PIM cores, and each core access local data from the DRAM bank, right? So this is the only assumption that we do. So in case that there is a new PIM memory module that still has basically these basic characteristics, it is one core per bank or per a few banks, and it is a distributed memory model, then PyGim can still work with that.
Yeah. So my question is, what about the locality, the spatial locality of each DRAM bank? Where the data, and will the data, have high spatial locality? It can be stored in each DRAM bank and could be reused frequently by the corresponding PIM cores. Is that the case here?
Yeah, I think that this is both the case in both 2D or 3D PIM architecture, and basically this is what the tuner will basically find, right? The tuner will basically predict the path strategy that gives the best performance. So this spatial locality will basically taken into consideration to some extent on the path predictor.
Yeah, okay, thank you. So I would say that the 3D may be a promising hardware to accelerate the graph applications. If yeah, thank you.
Sure, thanks.
Any other questions? I guess no. Thanks a lot, Christina. We enjoyed your talk. I learned a lot personally. So yeah, I wish you all the best and hope to have you for future talks as well.
Yeah, thanks a lot. Thanks for the invitation. It was a great pleasure for me. And yeah, hopefully we'll have more live seminars in the future. Thanks,
Yeah.
everyone.
Thank you. Bye, everyone.